to the soil mechanics lab. This course is offered in conjunction with the soil mechanics course. In this class, we are going to use a laboratory method to determine the properties of soil. Soil is like any other engineered material like concrete, wood, or steel. We need to determine the properties because when we do design, we need to know the properties of this soil. So in this class here, we are going to determine the physical property and engineering property of soil. In the first two lab sections, we are going to use different methods to determine the physical properties. More specifically, we are going to determine the grain size distribution, which is a curve that tells us the distribution of different soil particle size. In addition to that, we are also going to determine the specific gravity, plastic limit, and liquid limit of soils. These four parameters are physical property. They are just some index parameter that can tell us what kind of material we have. And then these properties are also, will also help us determine the classification of soil. In the future, we are also going to determine the engineering properties which will be used in design. More specifically, we are going to determine the hydraulic conductivity, how easy fluid can travel through soil. Okay, so that's the meaning of hydraulic conductivity. And then in addition to that, we want to know compressibility, which means that how much settlement will likely for a particular soil to have. And then lastly, we are going to determine some shear strength of material. So in the design of foundation, you need to know the shear strength of material because you want to know what kind of foundation you need for a specific soil type. Okay, so all of these parameters or properties will be determined in this class here. So in the upcoming 7 lab sections, we are going to do that. So before we start today's lab, we are going to talk about the principles of the labs that we're going to perform. First of all, maybe all of you have seen this in your soil mechanics course. This is a cylinder that contains soils with different particle size. Okay, if you look at it from the top, okay, we have very fine soil particles. Okay, so if you look at it closely, they are like the dust in the air. Okay, so the soil near the top have very small particle size. And then in the middle part, we have some soil particles that is similar to the beach sand that we have encountered at the beach. And then near the bottom, we will have some large gravels. Okay, so in terms of the size of the particles, the soil particles at the top is the smallest, and then the one that is near the bottom has the largest size. So today, okay, we are trying to find ways to figure out, okay, the soil particle size, more specifically the distribution of the soil particles. If you look at this graph here, this is the so-called grain size distribution curve. Basically, it's a curve that displays the distribution of the soil particles. If you look at the axis, okay, the y-axis is the percent finer by weight. Okay, so how many particles are finer than a particular sieve? Okay, the percentage of which is indicated on the y-axis. On the x-axis is the particle size itself. If you look at it closely, okay, this axis is in the descending order, meaning that the one that is near the origin would represent the particle that has the largest size. The one that is on the right-hand side of the axis actually means that the particle has a smallest size. And then usually we will display or use the log scale for the x-axis. The reason is different particle size. For example, for gravel, it has a particle size that is much larger than the size of the particle in this region. So in order for us to include everything on the same graph, we will need to use the log scale, because the difference in the particle size can be tens and 100,000 times. Okay, so because of that, we will use log scale. And then in addition to that, in our lab, we are only going to be able to determine the distribution of the particle size in this region. Okay, this region, for example, in tomorrow's lab, you are going to use some sieve to determine the particle size in this region. Basically, isolate the sand particle parts, okay, from the specimen, and then for the particle that is finer than the sand, we will use the hydrometer test to determine the distribution. For the hydrometer test part, you are going to do it today. And then for the gravel, because they are large particle, soil with large particles, actually we are not going to do that in this lab. Okay. Honestly, what we have to do is, in the field, we will need to first filter out all these large size gravel by using this field sieve. Okay, so before the specimen comes to our lab, we will need to first use the field sieve to filter out particle or soil particles that have a size that is greater than the sand. Before we move on to the hydrometer test, let's look at the sieves that we're going to use. This is a set of sieves. Okay, they should be arranged in this order, meaning that the one at the top, okay, the one at the top has the largest opening. The one that is at the bottom has the smallest opening. Okay, for example, this is the number 200 sieve, okay, which is indicated here. So, so what you have to do is to place some soil here in the beginning, and then shake it for 10 to 15 minutes, and then observe or determine the weight that is remaining on each sieve after the 15-minute shaking. So that's how we do the sieve analysis. For the particles that is finer than the number 200 sieve, it will be retained on a collection pan like this. Okay, so for the particles that is retained in this pan, we are going to use the hydrometer test to determine the distribution of the particles. It is because if we use shake it through finer sieve, there may be some dust particle that will vanish, meaning that some particles may be lost during the shaking process. So we will need to use the hydrometer test instead of shaking the particle through a finer sieve. Okay, so so that's how we are going to proceed with the finer particles. So for this part, okay, we are going to perform the hydrometer test. So basically, if you look at your soil lab manual, page 12, it consists of a list of test procedures that you will need to do for the hydrometer test. Basically, the key principle for the hydrometer test is we want to observe how the soil particles would settle. Okay. So the settling velocity of the particle depends on the size of the particles. If you use Stokes' law, okay, basically what it tells you is if you have a soil particle like this, okay, there are several forces acting on that soil particle. One, the downward force would be the gravitational force, the weight of the due to the weight of the solid, and then there are two other forces. One is the buoyant force, which is related to the volume of the particle, and the other force that is acting on the particle is the friction or the some resistance force that is acting on the particle, which is related to the velocity of the particle. So if you try to solve for the force balance of these forces, you will be able to derive the formula that is indicated on page 12 and page 12 and page 13. In your soil mechanics class or in your soil mechanics textbooks, the derivation of these formulas will be included. So in this class here, we're not going to derive it. You may want to refer to your soil mechanics reference textbook to take a look at the derivation. So in this lab, we are going to measure several quantities during the hydrometer test. So first of all, we have the parameter P. If you look at page number 12, P is the percentage of soil remaining in the suspension. It depends on several parameters, which are R, A, and M sub D. R is related to our hydrometer reading. If you look at page number 12 at the very bottom, capital R is equal to the difference of two small r. The first R is the hydrometer reading. When you for a cylinder of suspension with your soil particles. R1 is a reference hydrometer reading for the deflocculating agents. So basically you will need to take the difference between them, and then we will do that in a moment when we do the laboratory test. And then for A is a correction factor. If you look at table 2.2, which is on page 16, is a correction factor for the hydrometer reading. At this point, if you look at the table, if you look at the values of A, it depends on the specific gravity. However, when we first perform the hydrometer test, we do not know the specific gravity of soil. So that's why in this class, the second part of this class is to determine the specific gravity of soil, such that you will be able to use this table to figure out the appropriate correction factor A. So like what I said, we will go over how we will do determine specific gravity in the second part of this lab. And then for M sub D, M sub D is the mass of the soil which we are going to give you. So it would be some predetermined value. So you don't need to worry about that. You only need to record what R is during the test, and then also through specific gravity figure out A. In addition to the parameter P, you also have parameter D, which is related to K, L, and T. K is a correction factor, which depends on temperature and specific gravity. If you look at page 17, for a particular specific gravity value and temperature value, you will have a specific K value. So all you need to do is first, through the second test, determine the specific gravity, and then we will also record and measure the temperature. So based on those two information, we will be able to determine the appropriate correction factor K. All right, so in addition to the parameter K, you also need L and T. T is a time elapsed, so it will be in units of minutes. For L is basically the effective length or effective depth. So the parameter L is basically the distance between the fluid surface and then also the centroid of the hydrometer. So it will be the distance between these two levels. However, okay, if you go to page, let me see. Okay, if you go to page 18, okay, this effective depth, okay, or effective length parameter is depending on the hydrometer reading. Okay, so it varies, and then the hydrometer reading will affect the values of effective depth. Basically, what it means is when you place the hydrometer in this cylinder, okay, the reading that you measure or record is actually different from what should be the actual hydrometer reading. So what I'm trying to say is this may be the fluid level that you observe, but the true value, okay, the true value may be somewhat different, okay, something like that. Okay, so in this page 18, we have a table that allows you to make correction for that. So what you have to do is, based on whatever hydrometer reading that you have, you can figure out the effective depth from the table. And then in addition to that, for hydrometer, if you look at the page 9, you will see that the hydrometer that we are going to use is model ASTM 152H. Okay, so on page 18, you should use the values for 152H rather than 151H, because a different correction would be needed, okay, if you use a different hydrometer model. L, K, and T, R, and A can be determined through the laboratory test or hydrometer test. So, so in a moment, okay, we will start doing the test, because I think we will have very limited amount of time, and then we want you to leave on time. So we will start the demonstration in a moment.